What if I told you that the weather app on your phone showing a 75% chance of rain tomorrow isn't just pulling numbers out of thin air? Or that those stock market predictions with upper and lower bounds aren't just there to cover the forecasters behind? Have you ever wondered how we know if these prediction intervals are any good? Too wide and they're basically saying something will happen tomorrow. Too narrow and they're constantly missing the mark. Today I'm going to show you the secret sauce that data scientists use to evaluate prediction intervals. It's called the Winkler Score. Don't worry if you've never heard of it before. By the end of this video, you'll not only understand what makes a good prediction interval, but you'll have Python code that can evaluate these scores for your own forecasts. And trust me, understanding this could be the difference between a forecast that gets ignored and one that drives real decisions. Before we take a look at any formulas for the Winkler score, let's consider an analogy from darts. Imagine two dart players. Player A throws darts scattered widely, but they always hit the board. So there's a fairly wide interval. Player B throws darts, some of which are clustered tightly around the centre of the board. However, two of the darts miss entirely. The Winkler score rewards player B if their tight clustering outweighs the occasional misses. This is just like how a good forecast prediction interval balances precision and coverage. You can think of the Winkler score as the width of the prediction interval plus a penalty. We only apply that penalty if our observation, our ground truth value, falls outside of the interval. The penalty is proportional to the distance of that observation above or below the interval and alpha. We compare forecasting models using their Winkler scores, and the smaller the Winkler score, the better. Here's the formula for the Winkler score. Don't worry, I will show you how to write this in code as well in a moment. Alpha just stands for the 100 1 minus alpha prediction interval. So for example, if I wanted to calculate the Winkler score for an 80% prediction interval, I would specify alpha as 0.2. In these equations, U stands for the upper value within the prediction interval, L stands for the lower value, and YT stands for our ground truth observation of the time series within our test set. So we can see that what the Winkler score does is it breaks up the calculation into the width of the interval and then a penalty term. What you should also be able to see is that as that deviation from the interval increases, so does the penalty. The second thing you should be able to see, that as alpha becomes stricter, the bigger this value becomes. So for example, if alpha was 0.2 for an 80% prediction interval, this would equal 2 divided by 0.2, which would give you 10. If it was a 95% prediction interval, you would have 2 divided by 0.05, which would give you 40. So we will only calculate a penalty term if our ground truth observation falls outside of the upper prediction interval or the lower prediction interval. So we could have a prediction interval which completely covers all of the points within our test set. And in those circumstances, the Winkler score would be evaluated to be the width of the interval. Okay, so let's have a go with the Winkler score to compare some models on real data. All of the Python code I go through today will, as always, be available on GitHub. I'll link that in the description below. If you find any of the materials useful today, perhaps you could smash that like button and subscribe to the channel. So there's a few packages I'm going to use in today's video. The first is pmdarima, as that's going to allow me to use an auto ARIMA function and the ARIMA class. I'm also going to use some functions from my own software forecast tools. Those are going to be pretty simple. They're going to load some data. So I've got an implementation of the Winkler score here. I've got a plot time series function so we can visualize some of what's going on. And I've got a seasonal naive benchmark model that we can use to compare to the ARIMA models. So in this video, we'll use emergency department data from the UK from the year 2017. We've got a lot of training data, but we're going to hold out 28 days of the time series, which will act as our test set. That's going to contain our ground truth observations that are going to be used to calculate our Winkler scores for various models. So let's load the emergency department data. That's pretty simple data. That's count data of the number of arrivals to an emergency department in the UK during 2017. And we'll perform a train test split on that data where we hold out 28 days of the time series. And we'll use that as our test set. And that will be what we will compare our prediction intervals against. So my plan is to create a benchmark model, a really simple model that's called seasonal naive, that's just going to carry forward the last 7 days of the time series as our prediction. And we'll compare that to 2 ARIMA models. For both types of models, we'll generate their 80% prediction intervals over the 28-day period. And then from that, we'll calculate their Winkler scores and compare the models and choose the model with the smallest Winkler score. So the first model I'm going to create is a seasonal naive model with a period of 7. I'm going to fit that model to the training data. I'm going to predict 28 days into the future, and I'm going to return the prediction intervals. And by default, the seasonal naive model returns the 80% and the 90% prediction intervals in a list. So we have a tuple that's returned the point forecasts and the prediction intervals. So this is the output of the seasonal naive model. The point forecast is shown in red. We can see that is a repeating pattern. Indeed, that is just the last 7 days of the time series carried forward. The 80% prediction interval is the shaded region in light red. We can see that gradually gets wider the further we go forward into the 28-day forecasting period. So that's representing an increase in uncertainty within the model prediction. The test data are black dots, and we can see actually that all of those dots are covered by the prediction interval. So the Winkler score in this case would be the width of the interval. Let's create 2 simple ARIMA models and compare their prediction intervals to those from seasonal naive. In pmdarima, we have access to the ARIMA class. And to create a pre-specified model, all we need to do is pass in the order. You can see here that the first model I'm creating is a super simple model. There's a single autoregressive term, and I'm going to take the first difference of the data. I've called that model M1. I'm going to fit that to the training data, and then I'm going to call the M1 model's predict method. I'm going to specify that we go 28 days into the future, and I'm going to ask it to return the confidence interval. I can assure you what pmdarima means is a prediction interval. And I'm going to specify alpha as 0.2 so that it returns an 80% prediction interval. Like seasonal naive, that returns a tuple. So we have the point forecasts, which I'm storing in ARIMA M1 preds, and we have the 80% prediction intervals. For the second model, I'm going to allow the auto ARIMA model to search through a selection of models and decide which is the best based on the lowest AIC. And then again, just like the simpler ARIMA model, we'll call predict and specify the same parameters. So here's a visualization of the ARIMA 110 model. So again, the color coding relates to the data we're displaying. So the red line is the point forecast, and the shaded light red area is the 80% prediction interval. Now we should be able to identify straight away that we have 100% coverage of the test data, just like with the seasonal naive model. However, in the case of the ARIMA model, we can see that that prediction interval becomes very wide indeed by the end of the 28 days. So what we should intuitively expect is that the Winkler score is larger for the ARIMA model than the seasonal naive. The ARIMA function has returned something a little bit more interesting. Now we have a fairly narrow prediction interval, at least relative to the seasonal naive and ARIMA model. But we have points that now fall outside of that 80% prediction interval, as we should expect. So the question is, how far are those points away from the interval, and does that mean they incur a penalty, which means that Winkler would prefer the seasonal naive model over our auto ARIMA model? So let's calculate the Winkler score for those three models. The forecast tools package includes a Winkler score method. We just need to pass in the test data and the intervals for the model we're interested in, as well as the alpha value. So we can see, for example, that seasonal naive has a Winkler score of 91.22. Within this repository, I've included a function called test set summary table. That's going to generate a nicely formatted table of results for those three models so you can compare the Winkler score. It also includes the mean absolute error. So if we look at that first across the three models, we could see that we would actually pick the seasonal naive model if we relied only on point forecasts, as that is a May of about 18 compared to the second best May, which is about 22 people. But when we look at the Winkler score for the 80% prediction interval, we can see that we would prefer the auto ARIMA, as that beats the seasonal naive model by some considerable margin. Now, the Winkler score also contains a parameter called return scores. If we set that to true, we'll instead return a dictionary which contains the individual Winkler scores from each of the time periods within the test set. Some of those numbers represent the width of the prediction interval. The larger numbers in there represent scores where we have the width of the prediction interval plus the penalty term. So those are the observations that fell outside of the interval. So the Winkler score is actually the mean of all of those values. So all we need to do to get back to our original value is take the mean of that array, and we get back to 77.26 for the auto ARIMA model. So maybe you want to write your own Winkler score code. Good news, that's really simple to do. I recommend checking out Forecasting Principles and Practice, which is an online resource written by Hyndman and Athanasopoulos. It's a great book. It's not in Python, it's in R. However, I highly recommend checking that out. We'll have a look at a one-step example from that book and how you implement that in Python. So in this example, we have a one-step ahead prediction. And that gives us a prediction interval between 773 and 744. The actual observation, the ground truth value, was 741. So we can see straight away that fell below our 80% prediction interval, which means that it should incur a penalty. So the example in the Forecasting Principles and Practice book shows that we should expect to obtain a Winkler score of 55.7. Let's just check that the forecast tools implementation of the Winkler score works as expected first. So we've got our parameters here in Python code. We'll pass those to the Winkler score function. So we have the observation, we have the 80% interval, and we have alpha equals 0.2. Great, that returned 55.68. That's a relief. So the way we would implement that in Python code is we would first calculate the penalty term. So remember that was proportional to 2 divided by alpha multiplied by the difference between the observation and the interval. Our interval width is simply the difference between those two interval values. So our score is then just the width plus the penalty, and we print that out to get 55.68. For a multi-step example, I recommend making use of NumPy arrays, as this allows us to perform some vectorized operations on the data and very efficiently and very simply calculate the correct Winkler score. So I've provided you a Python function here called hstep Winkler score. That's going to accept a NumPy array containing the ground truth observations For example, a NumPy array of length 28 that covers all days within that test set. We'll then have a multi-dimensional NumPy array which contains the prediction intervals. So you can think of that as 2 columns of data. And then we have a float value, which is our alpha. So for example, 0.2 if we were calculating an 80% prediction interval. Now, just to warn you that this function does not contain any form of validation for these input values. Experience tells me that if you are producing a function like this, you should include some validation to make sure that things are being calculated as expected. Trust me, things go wrong. I do recommend that. So the function is written using NumPy vectorized operations. The first thing we do is calculate the width of all of the intervals within the forecast period. So effectively, we've got all rows of the data in column 1, which will be the upper bound, and all rows of the data in column 0, which is the lower bound, and we take the difference of those and we have a NumPy array containing the widths of the interval. We're then going to use Boolean indexing to create masks for the data, true and false values, where we know that the observation is below the lower interval or the observation is above the upper interval. We'll then initialize our penalties. So the first thing we'll do is we'll calculate our penalty factor, which is 2 divided by alpha. We're going to have 2 arrays representing the penalties we give a t-value above the interval and 1 below. If we found any observations that were below the lower interval, what we'll do is we'll multiply that penalty factor by the values that were below and subtract the true value. This is where the mask comes in. So we're only going to return the intervals that were below the value, and we've done that doing Boolean indexing. We'll do the same for above the mask. So any values that were above the mask, we'll subtract the interval value and multiply that by the penalty factor. And then finally, we add up all of those NumPy arrays. So we have scores equals widths plus penalties. So remember, we've got 3 NumPy arrays. We've got the widths, then we're adjusting the penalties that are below, and then we're adjusting the penalties that are above. And we're only going to return the mean, so we take the mean of that NumPy array. So let's test that code out. So the first thing I'm going to do is recreate my seasonal naive model. I'm going to fit that to the training data. I'm going to predict 28 days ahead. I'm going to return the prediction interval, and then I'm going to call my h-step Winkler score, my custom Winkler score function, and then I'll print out the score rounded to 2 decimal places. In the description below, I'll link to Forecasting Principles and Practice, which in my personal opinion is the best forecasting book ever written. But maybe you're someone that's struggling with the absolute basics of forecasting, including performing a train test split of time series data. If so, this video on the screen right now is for you.